Hello students. Today we are going to learn Newton-Raphson method. So basically the Newton-Raphson method is also known as the method of tangents, and it is one of the fastest iterative method. This method begins with one initial approximation, but here we have to take due care while selecting this initial approximation, as it is very sensitive to the initial approximation. So once a proper choice is made for the initial approximation, it converges faster than false position method and the other methods. So basically there are two ways to derive the formula for Newton-Raphson method. One method is through the geometrical interpretation, and other is through the Taylor series. So first we will see the Newton-Raphson method formula, how we can derive it using the geometrical method. So in geometrical method, we consider a graph like this. This graph we consider f of x. Then we assume that x1 is an initial approximate root of f of x is equal to 0. Then at this, what we do is at this point we draw the tangent. Say suppose here we are having the point f of x1, and at this level the coordinates of this point will be x1 and f of x1, because from here we are having this as x and this is f of x. So say this point is equal to x1 f of x1, or the coordinates of this point will be x1 f of x1. Now let's suppose that we draw a tangent at the curve f of x at x is equal to x1, and this tangent intersects the line at x2. So now the slope of this tangent will be given by tan of gamma will be equal to f of x1 divided by x1 minus x2. How this will be equal to f of x1 divided by x1 minus x2 is like we are calculating the slope of a tangent, and you know the slope of a line joining two points is given by y2 minus y1 divided by x2 minus x1. So suppose if we are having the 2 points, point P1 is x1 comma y1 and point P2 is x2 comma y2, then the slope of this line, or we can say the slope of the tangent, that is given by y2 minus y1 divided by x2 minus x1. So here our y2 is f of x1, because we are considering this y line or y-axis as f of x. Therefore this will be equivalent to f of x1 minus, here we have f of x2 as 0, so it will be equivalent to f of x1 minus 0, so I am not writing here 0, and divided by what is our x2. We have here x1 as our x2 and x2 as our x1, therefore it will be x1 minus x2. So let us suppose this is equivalent to f dash of x1, where f of x1 is the slope of f of x at x is equal to x1, right? So when we solve this for x2 value, this will be equivalent to x1 minus f of x1 divided by f dash of x1. So we are basically solving this equation for x2. When we solve it for x2, it will be equivalent to x1 minus f of x1 divided by f dash of x1. So then at x1 again, if we are considering the point x2, and again we are calculating the things like we are drawing the tangent again, and it is coming and it is intersecting the x in axes at some point, say suppose x3, then we say that x3, similarly this x3 will be equivalent to x2 minus f of x2 divided by f dash of x2. So when we generalize the term, we will have xn plus 1. So xn plus 1 term will be equivalent to xn minus f of xn divided by f dash of xn. So this method of successive approximation is called as Newton-Raphson method, and this process will be terminated when the difference between two successive values is within a prescribed limit. So when we actually solve the question using the Newton-Raphson method, we will be given with some prescribed tolerance. So when we will evaluate the successive iterations, when the error, or we can say the absolute error, will come within that prescribed tolerance, we will say that our root lies at that point. So that we are going to take in our next lecture. In this lecture, we will simply see how we can evaluate the formula for Newton-Raphson method. So this was how we evaluated the formula for Newton-Raphson method using the geometrical interpretation, in which we are considering the points and we are just drawing the tangents on them, and we are calculating the slopes at every intersection points. Next way for Newton-Raphson formula is we derive it using Taylor series. Let f of x is equal to 0 be the given nonlinear equation, and x0 be the initial approximation, and h the correction to x0, so that f of x0 plus h will be equivalent to 0. So we are considering f of x is equal to 0 is our given nonlinear function, and then we are considering x0 to be the initial approximation or the initial approximation of the root, and then on that root we are taking this h as the correction. So therefore we can say that f of x0 plus h will be equivalent to 0, right? So we can say that f of x0 plus h will be equivalent to 0. So then we expand it using the Taylor series. Basically, Taylor series is a representation of a function as an infinite sum of terms that are calculated from the values of the function derivatives at a single point. So here we have f of x0 plus h, and we are trying to expand it using the Taylor series. When we expand it using the Taylor series, this will be equivalent to f of x0, the first term, plus h f dash of x0, where this f dash is the derivative of the function. So it will be equivalent to h f dash of x0, and h divided by 1 factorial. 1 factorial is equivalent to 1. Therefore, I am not writing here 1 factorial. So it is directly coming as h f dash of x0 plus h square divided by 2 factorial f square x0 plus the next term, if I will write, it will be h raised power 3 divided by 3 factorial f of 3 x0 and so on. I am taking it up to the nth term, so here it will be h raised to the power n divided by n factorial f of n x0. So this is how we expand the term using the Taylor series. So all these f dash of x0, f2 of x0 and fn of x0, they are all the first order, second order, third order and nth order derivatives of x0. So this is basically how we derive in the Taylor series. So if we neglect the terms containing the second order and higher order derivatives, say from here we are neglecting the terms, these terms we are neglecting, so we will be left with only these two terms. So our formula will be, then therefore we will get f of x0 plus h will be equal to f of x0 plus h f dash of x0, because all these terms we are neglecting because they are the higher order derivatives, so we are neglecting them. So if we get f of x0 plus h will be equal to f of x0 plus h f dash of x0. So if we say that f of x0 plus h is the root of f of x, if you remember that we have taken the function as f of x0. So if we say that this f of x0 plus h is the root of f of x, then we can say that f of x0 plus h will be equivalent to 0, because we are considering a function, let f of x is equal to 0. We are considering this function, we are considering it as 0. Therefore, this function will be equivalent to f of x0 plus h will be equivalent to 0. So therefore we say that f of x plus 0 is equal to 0. That will be equivalent to f of x0 plus h f dash of x0. This. So basically this whole is equivalent to 0. So we are considering it here. We are considering it as f of x0 plus h f dash of x0 is equal to 0. So then we solve this for h. As actually we have put this h as the correction to x0, so we are basically concerned with this h here. So we will evaluate this for h value. So here h will be equivalent to minus, if we will take this term from this side, it will be the negative term, so it will be minus f of x0 divided by f dash of x0. So h will be equivalent to this, right? So therefore if x0 is the initial approximation, by adding to this the value of h, we get the next approximation to the root. So x0 we have considered as an initial approximation. That means if we correct this, if we add the value of h to this x0, it will be equivalent to x1, because h is the correction to x0. Therefore we say x1, our next value, our next approximation will be x1, which will be equivalent to x0 plus the correction over x0. So h we have already calculated, we are putting the value of h here. So it will be equal to x1 is equal to x0 minus f dash of x0 divided by f dash of x0. We are putting the value of h here in this equation. The value of h is this, we are just putting it here. So therefore the next approximation, which is x1, will be equal to x0 minus f of x0 f dash of x0. Similarly, if we will calculate it for x2, that will be equivalent to x1 minus f of x1 divided by f dash of x1, where f dash is actually the derivatives. So in general form, the ith approximation will be equivalent to xi plus 1 is equivalent to xi minus f of xi divided by f dash of xi, right? So the iterative procedure, this is actually the formula for the Newton-Raphson method. This is basically the iterative formula. So the iterative procedure terminates when the relative error for two successive approximations becomes less than or equal to the prescribed tolerance. So basically in today's lecture we saw how to derive the formula for the Newton-Raphson method using the geometrical method, and the other method was using the Taylor series method. In our next coming lecture we will try to solve a question or a nonlinear equation using the Newton-Raphson formula. So thank you for today's lecture.